Hello there, I'm Mr. Rose, and we're going to continue with our examples today about Gauss's law, or with Gauss's law. And for our next example, we're going to talk about a non-uniform field traveling through a geometric cube. Again, as always, I'm going to recommend that you read our example. You try and go ahead with me before you just watch me solve out the problems. All right, so I've outlined our problem here with our non-uniform electric field, 3.0 x I hat plus 4.0 j hat newtons per coulomb. Notice I have this x component here, but I have no y here, even though I have an x and y component, or an I and j component. See if I can focus that a little bit better. Hold on. That looks a little bit better. All right, and it's traveling through this Gaussian cube with its base at 1 and 3 in the x direction. So I've already drawn out our coordinate system. Now I'm just going to quick sketch out our cube here. And that'll serve as my Gaussian cube. Now what we're going to look for here is we're actually going to find the flux. And can you figure out which sides we're going to look for? We're going to find the flux in the left, the right, the top, and the bottom of the cube. I don't need to worry about the front face or the back face, and that's because that's in our z direction, and we can see ij, I have no k component, so I have no z direction of flux. I already know the flux going in and out of the page, or in this z direction, is 0. So what I'm going to do is I'm going to break down each part. I'm going to first start with the right face. So I'm going to just sketch again my right face. And on that face, I'm going to put my area vector, dA. So from there, I'm going to apply my Gauss's law. I know that flux is equal to the integral or antiderivative of E dot dA. So that's going to tell me that my flux is equal to just straight plug in a formula right now in my ijk direction, 3.0 x in the I hat plus 4.0 j hat dot dA in the I hat direction, because in my picture it's going in that I direction. Just trying to make sure that everything's fitting on the screen here. So what are we going to do, and what do we notice? Well, I know that my right face, I do have an x value. At my right face, this value, I know that x is equal to 3.0 meters. That's going to become important. So I'm going to separate out my dot product. I'm going to say is equal to, my flux is equal to the derivative of 3.0 x dA in the I, drop my I hat, in the I hat direction. So that I and that I are going to dot against each other, plus 4.0 j dot dA in the I hat direction. Now I know I and j, or j and I, those are 90 degrees, and I know in a dot product that 90 degree goes to 0. I know in a dot product I dot I is going to be 1. I'm going to pull out my 3 here. So now I have the flux is equal to 3.0 times the integral of x. I know my I dot I is 1 dA. Well, that x is 3 as we set up here. So I can pull that out. Now I have 3.0. Now don't be confused. X is not the variable that I'm integrating on. I'm integrating about dA. So that's just actually a constant at that right face times the integral of dA. And what's dA? dA is the area. Well, I have an area of a square. My square is 1, 2 by 1, 2, or 4 square meters. The integral of dA is just A, where A is equal to 4 meters squared. So I would have my flux equal to 3 times 3 is 6 times my area of dA, my integral rather of dA, which is just A, which is 4. 3 times 3 is not 6. 3 times 3 is 9, which is equal to 36. And then our units, if I kept my units out, but I know my units for flux, I have meters squared, I have newtons per coulomb, so I have Newton meter squared per coulomb. That is the flux going through the right face of this cube. All right, so now we're going to try something similar for the left face. The left face you should be able to go ahead and do on your own. I know x is at 1.0 meters, and I know for my face that's constant, that's not changing. I'm going to rewrite my electric field here. My electric field was given to us as 3.0 x in the I hat direction plus 4.0 in the j hat direction. And we are going to apply Gauss's law. I'm looking for my flux. I'll designate a little L so I know I'm at the left side. Let's try and get that focused again. I know I'm at the left side of my cube is the integral. Now I keep putting this surface integral because I know even though I'm doing one piece at a time, this still is technically a surface integral because it's all the flux that's going through the surface of that cube. So my integral of E dot dA. So I know my flux at the left side is equal to E, which is again my electric field, 3.0 x I hat. And I'm going to separate it right out this time. If you didn't draw it and you're confused on what is going to be different, let's put a little sketch over here. It's harder for me to draw the left side. So that actually looks like a right side, but I can't do any better. This time my dA is in that direction. That's going to be important because my electric field obviously isn't changing, but what is now changing is the direction of dA. This is going to be 3.0x in the I hat dot my dA, that's actually going to be a negative dA in the I hat direction. And we're going to obviously add that to the integral of 4.0 j hat plus dot negative dA in the I hat direction. And I already know when I dot I and j, that is going to be 0. So I squeeze that in on that side of the paper. That's all right because we know it cancels out to be 0. Now this is going to be the same thing. It's almost the same we just saw, except now that negative sign is going to play an important role. So again, I'm going to pull out my 3. I know the flux is equal to, pull out my 3. I have x I dot I is just going to be the unit vector of I dot I is going to be a 1. So I know that comes out to be just x dot dA. I know that x this time is not 3, this time it's 1. So I know my flux is equal to 3.0 times 1.0 times the antiderivative of dA. And I know when I sum up all those dAs, that's just A. And again, we know our area is just, pause for you, the area is just 4 meters, up 4 square meters. So I know the flux about the left-hand side is 3 times a negative 4, which is equal to negative 12 Newton meter squared per Coulomb. Now I'm going to do the top face. And the top face is going to be a little bit different because now I'm in the y-hat direction. So I know my flux about the top, I'll write a little bit bigger. My flux about the top is equal to, again, the antiderivative of E dot dA. And you should know what to do here. My flux about the top is equal to, I'm going to rewrite my entire field here, 3.0x in the I-hat plus 4.0 in the j-hat direction, dot. Now the top face is easy to draw. My dA is going in the positive j-hat direction, so that's dot dA j-hat direction. And again, we're going to distribute and do these individually. About the top, my flux about the top is going to be 3.0x I-hat dot dA in the j-hat. 3.0 I-hat dot dA j-hat plus 4.0 j-hat dot dA j-hat. Just like we saw before, I dot j are 90 degrees with each other, so that whole thing is 0, and now I'm just left with this 4.0 j dot daj. I can take my 4 out. I'm going to take the integral of dA. Well, the integral of dA, again, is just a. And even though it's a top, it's still the same size. It's still got an area of 4 meters squared. So I know the flux about the top is, I pulled out that 4. I'm taking the antiderivative of dA, which is just a, where I know a is equal to 4 meters squared. Therefore, the flux through the top surface is 16 Newton meters squared per Coulomb. Now, I'm going to stop here. I'm not going to do the bottom face. And I want you to think about, do I need to actually do the bottom face? Well, given my electric field, I know my x cubed. Let's go back to my drawing from the beginning. My cube, my left face and my right face are different. So I have different flux, my left and my right face, and I have dA going one direction for the top, dA going the opposite direction for the bottom. I'm sorry, for the left and for the right. For the top and the bottom, I'd have a dA going in different directions as well. But what about the actual size of it? Since I have a different x and a y, but the top and bottom are in the exact same places. So the only difference between the top and the bottom would be what? Should be either a positive dA or a negative dA. So my flux coming out the bottom, mathematically, I would have 4.0 j dot negative dA in the j-hat. My x component should still cancel out, which means my flux from the bottom should just be negative 16 Newton meters squared per Coulomb. That's, hold on. That's all I have for you for this example. Please feel free to like, comment, and subscribe, and you'll see me next time.